All right, you ready? This is the last new piece. If you've been looking at your study guide, perhaps there was something on the very end, the very last line that you're like, wait, Mr. Hess, what are these 5 types of reactions things? That's the last piece we have to talk about. So you ready? This is in chapter 9.2 if you decide you want to follow along with me. I'm not going to use a textbook, but it is in 9.2. There are 5. You can take all reactions and basically put them into 5 categories. Now, those categories can overlap. Like sometimes a reaction is more than one. But for the most part, we can categorize them into these 5 types. Does anybody know any of them? Sir? It's in 9.2. I don't remember the page, to be honest. 280 what? 289. So the first one is what we call synthesis. Synthesis is where I take one something, I add it to another something, and I produce a third something. 2 become 1. You will find that I have relationship metaphors for all of these lovely reactions. So what do you think this relationship would be? It would be marriage. Love. True love. Right? Princess Bride. 2 become 1 is synthesis. Pretty straightforward, right? Number 2 would be decomposition, where I have 1 and it breaks apart into 2. And of course, the opposite of that would be divorce. Okay? You had something that was together and it broke up into smaller pieces. Now, please understand, I can have a synthesis reaction with 3 or 4 or 10 things that all come together. I can have decomposition where one something breaks into 15 somethings. The point is you went from less complex to more complex for synthesis. You went from more complex to less complex in decomposition. Does that make sense? And these are opposites, obviously, right? Good. I can't have something that is both synthesis and decomposition. That doesn't quite work. Number 3. Number 3, your textbook uses this term, the replacement. Replacement reactions. And I divide those into 2 pieces. The previous textbook I taught from divided into 2 pieces, and I think it makes a little more sense if we do it that way. Right. The first is what we call a single displacement reaction. And the second is what we call a double displacement reaction. So in actuality, if I wanted to put numbers on these things, I would put them here. That would make a little bit more sense. So a single displacement reaction is very easy to tell. You've got a compound, and then there's an element all by itself. And when the reaction occurs, the single element breaks apart the compound and partners up with one of the pieces and leaves the other one all by itself. So if C is a metal, it's going to kick A out of the way, because remember, in a compound, metal always goes first, right? So the C would kick out the A, so I would make CB, and then poor A would be all by himself. So this is that couple at school who has been together for a long period of time, and then the new guy shows up. Oh, and everyone's like, ooh, that new guy, ooh, they're pretty nice. And so the new guy comes, and he breaks up the couple, and he steals the girl. Single displacement reaction. You won't forget it, right? Double displacement's a little bit more funky. I've got 2 couples. Well, you see where this is going, yes.
Oh, no.
And both of these couples break apart, and they switch partners, and they come back together. So realize you have to do this correctly now. These are 2 metals, right? A and C are the metals. B and D are the nonmetals. So therefore, A goes with D, and C goes with B. Right? We've got to make sure you get the right partners, because these are two ionic compounds. Double displacement only ever happens with ionic compounds. Wife swap, there you go. That's definitely what it's just like. Yes, ma'am? No, it would be a metal and a nonmetal and a metal and a nonmetal. Right? Because A is a metal and C is a metal. So C is paired with B, which is a nonmetal, and A is paired with D, which is a nonmetal. Ionic compounds. Yep, both A, B, and C, D would be ionic compounds. And the pieces they produce would also be ionic compounds. We cool? Okay. Last but not least, this is the last one. Got to add myself a little more screen here. Number 5 is everybody's favorite, combustion. Combustion. So, for combustion, it doesn't fit into a nice piece. I don't really even have a good relationship metaphor for combustion. But you need a fuel. So that can be an element or a compound. And what do I need to burn something? Okay, we'll get to the spark in a second. Okay, you're talking about the activation energy. In order for something to burn, it needs something. It needs air, but more specifically, oxygen. So you have to have oxygen as a reactant when I'm doing combustion. So a fuel, some sort of element or compound, plus oxygen is going to react and produce an oxide. An oxide is simply a compound that has oxygen in it. Are you with me? Water, H2O, that is an oxide. Right? Carbon dioxide, that's an oxide. These are two very common products of combustion. So fuel plus oxygen produces an oxide plus energy. When I'm making a combustion reaction, the thing you all like about it is that it makes fire. It makes boom. Right? These are fun things. So, for combustion, I need a fuel plus oxygen, and it will make an oxide, a compound that has oxygen in it, plus energy. And the other thing about combustion is that it happens very quickly. So I'll put just a little arrow here. Oops. Quickly. It happens very quickly. You guys are all like cool, wealthy people. Does anybody's car or know of a car or have seen a car that has rust on it? Sure, right, okay. Okay, so do you realize that rust is almost exactly chemically to a combustion reaction? You have an element, in this case it's the iron, in the steel, in your car. It's reacting with what? The air, more specifically. The oxygen in the air, right? And it's producing an oxide. Does anybody know what that rust is, like its actual chemical name is? Close. Iron oxide, right? If you're going Latin, you'd have been correct. It's iron oxide. And there is actually energy that is released. If you were to put you can actually make a rusting reaction produce you energy. It's very slow, but it actually gives off, it's exothermic, it gives off some energy. So why isn't your car rusting? Why doesn't it simply blow up in the parking lot? Because it doesn't happen quickly. It's a very slow reaction. Does that make sense? So there are these 5 pieces with the combustion reaction. It must have a fuel, again, an element or a compound that will burn. It has to have oxygen. These are both our reactants. Its products will be an oxide, and it can be multiple oxides. It doesn't have to only be one. An oxide and energy. are the reactants, excuse me, are the products, and it has to occur quickly. Are you with me? Okay. Let's look at what you all did yesterday, and let's see if we can't assign what type of reactions these are. So this is from that number 75 that we did. If we're looking there, this is called naphthalene, this C10H8. It's what we call a hydrocarbon. Does anybody know any other examples of hydrocarbons? I'll give you a hint. It comes out of right here. Gas. It's a gas, sure, but more specific. Propane. Propane. Anybody know any other ones? Methane. Butane, right, like from your lighter, right? These are all what we call hydrocarbons. Are you comfortable those are all nicely flammable? Right? They like to burn. Okay? So, I've got fuel. I've got oxygen. Is this an oxide? Carbon, CO2? How about H2O? Sure. What's it missing? Energy. Now, sometimes they don't give you that. But are you comfortable? What kind of reaction is A?
Combustion.
It's combustion. This is a combustion reaction. Very common products, actually, the only products you ever get when you burn these hydrocarbons are carbon dioxide and water. Are we cool? How about B? Sorry? Oh, sure. I'll post it on school YouTube, but you're welcome to. Yeah. Okay, so look at B. So B, I've got hydrogen sulfide and magnesium chloride. Sorry, not magnesium, manganese chloride. And then I have manganese sulfide and hydrochloric acid. What kind of reaction do you think that is? So how do you know if it's single or double? Because I hear you all saying replacement. How do I know whether it's a single or a double? Good. Single replacement has an element all by itself. That's the key for single replacement. It's got some element just all alone that swaps places. So let's go back to that one. Are there any elements all by themselves in B? No. So therefore, what must this be? Double replacement or double displacement. Your textbook uses those terms interchangeably. Okay? So this is a combustion. And this guy is definitely a double D. Okay, how about C? Magnesium plus nitrogen produces magnesium nitride. It's marriage, right? But what do we call that in chemistry? Synthesis. Good. Good. Not marriage. Synthesis. Good. Exactly. If you put marriage on the test, that probably won't go over well. Okay, how about D? I've got oxygen difluoride that's breaking into oxygen and fluorine. What would that be? Decomposition. Does that make sense? Yes, ma'am. Yeah, I want you to know the names. Yeah, please. I'll put a smiley face. How about that?
Okay.
But I'll still mark it wrong. Yeah, you'll learn the names. There's no worries. It's smiley face at least, right? Okay, here's what I want you to try. Let's go to, Let's go to 7. Oh boy. Don't let me get rid of that. Why don't you try this? I want you to try 71. See if you can't tell me what all these problems are from 71. I'm going to stop the recording here. What kind of reactions are